So my talk will have a little bit of overlap with the incentive talk that was presented by Rinke and Wojtek in the morning. So there you will probably recognize some of the themes, but I would like to approach this set of problems from a slightly different angle. So what am I going to talk about? First, I'm going to outline what the challenges of persistency are. So basically, in a network of freely participating nodes, where every single node is operated potentially by a different entity following its own interests, how does it become possible to nevertheless ensure that the data that we upload to this very diverse and constantly reorganizing network, why it can still stay there and remain retrievable. Then I'm going to talk about swap incentives. So this is the part that is a little bit overlapping with the morning presentation, but I will more focus on the emergent behavior. So I will talk about what incentives we have in place and what we can expect to happen because of those incentives. Then I'm going to talk about protection against spam, and I use this word spam in the broadest sense possible. That's how people at Google use it. So basically, it's any content that you don't want. So it's not necessarily advertisement. It's anything that is unwanted content that takes up space, takes up bandwidth, and so on. And then in the last part of my presentation, I will go through a few use cases, possible use cases, or use cases that people are currently already working on, and see how they play out with the kind of tools that we have or that we're going to have. So let's start with the challenges. So the challenges are basically come from 4 different sources. The most important one is churn. So nodes are coming and going, they take some data with them. When new nodes join the network, then some content which they don't yet have is being searched, asked of them, and so on. So the fact that nodes are leaving and joining the network, it does put a stress on content, and it does make it more challenging to retain it and to locate it, and I'm going to talk about how we address this. The second one is spam. So what spam is in this context, it's content that it potentially crowds out other content. So even though we expect that Swarm will have many nodes, but no matter how many nodes Swarm has, its resources in terms of storage and bandwidth will always be limited. And if there's no bound on the content that is being uploaded, and there are some problems with the incentivization of that, then we can expect spam crowd out useful content, and I'm going to talk in detail about what we're going to do about it and what we're currently doing about it. Then there's opportunity costs. So again, because of the limited resources, in this case of one particular node, so they have some storage, they have some bandwidth, and they are making decisions individually. Each node or each node's operator is making decisions of how to use these limited resources, and by not using them for one purpose, by using them for one purpose, they're foregoing the opportunity of using it for some other purpose. And then finally we have incentive misalignments, which are again well-known problems in game theory and economics, so I will shortly go through them, how they affect Swarm in particular. So churn. When nodes leave, it's obvious how that is a problem because they reduce the redundancy. We have the same information in the network stored on fewer nodes. Nodes joining Swarm, they require time to what we call sync. So in Swarm lingo, syncing means obtaining all the data that will be eventually surged at your node. So in Swarm, the addresses of nodes and the addresses of data come from the same address space. It's a distributed hash table, that's what it means. Which means that your address kind of determines what kind of data you should store, what kind of data is going to be requested from your particular node. And what we call syncing is the process of obtaining that data. And if nodes join, it takes time while they sync, and during that time, they cannot actively participate in the network. They cannot serve requests. So from these two things, it's apparent that any changes in membership, be it nodes joining or nodes leaving, entails some kind of data movement. Something needs to happen because nodes. So as nodes come and go, data needs to be shifted around, and that particular process is what we call pool syncing in Swarm. So when you're reading Swarm documentation, pool syncing is the special kind of syncing that happens because there are changes in the membership of the network. And also we have this concept of the radius of responsibility, which is the kind of data, the kind of distance of data for which a single node is responsible. So if Swarm consisted of a single node, then its radius of responsibility will be infinite. So basically it would encompass the whole data space. But as more and more nodes join the network, this radius of responsibility is getting smaller and smaller, and as nodes leave, it's getting bigger, and those changes are the ones that need to be handled by the pool syncing process. Spam. So there are two kinds of spam. There's malicious spam and there's accidental spam. So in case of malicious spam, and I will talk about when some nodes might engage in malicious spamming, so it's an attack. It's an attack, it's performed by an attacker who has a specific selfish goal of obtaining some benefit at some other node's expense, and because of that they are pushing content to Swarm. They either want to do it for the purposes of censorship, or they want to get paid for something, and so on. So there can be malicious spamming objectives, and there's accidental spam. So basically, if uploading doesn't cost anything, then people might not be expected to be sparing with their upload activities, and they just might casually upload a few gigabytes, not caring about the consequences and the load that they place on the rest of the network. And one of the interesting challenges that we faced, and I think we did a pretty good job of resolving it, that it's really difficult to tell uploading from syncing. So in both cases, data is being moved, but in one of the cases, when you're uploading data, you're uploading content into the network that has not been there initially. In the other case, in case of syncing, you're just moving content around as necessary. And of course, the difference between the two is that syncing is something that is necessary for the continued retrievability of data from Swarm, whereas uploading is a service that for which the network, which will take more resources from the network, and therefore somehow the network needs to be compensated for it. But from a single node's point of view, a single node has a very limited view of the whole network. It is only connected to a logarithmic number of peers, a logarithm of the total number of peers. From a single node's point of view, it is really difficult to tell whether a chunk that is coming in is syncing or an upload. And as you can see from the arguments that I just highlighted, by misleading a node about the nature of the incoming chunk, you can really influence their. And so if uploads are free, then they might crowd out important data. And also censorship resistance and spam resistance, they are kind of at odds with each other to some extent, because if it's easy, so if there's some spam protection mechanism, then one avenue of attack, a censorship attack, is to somehow classify the content that you want removed or suppressed inside the network, is to classify it as spam. So on one hand, the network needs to be, it needs to be difficult to remove data that is uploaded legitimately. On the other hand, it should be easy to get rid of spam. And there's kind of a trade-off here, and I'm going to talk about how so now I'm just highlighting the challenges, but then I will talk about how we're actually meeting these challenges. So there's opportunity costs. I already talked about them. So basically there are two kinds of opportunity costs. One is storing swarm data versus something else. So you have a limited disk space and you want to allocate some of it for swarm and other parts of it for other things. Or even inside the swarm, inside the space that you allocated for swarm, there's a choice whether you store this data versus other data. And these all imply some opportunity costs, and there should be a clear way for each node to make these decisions in such a way that if they follow their own rational self-interest, the emergent behavior will be that they will actually work in the interest of the whole network. So the misaligned incentives are, so the problems caused by misaligned incentives are selfish storage, which is kind of an analogy with selfish mining, where basically by maximizing your profitability, you somehow are doing unnecessary work. So in selfish mining, if you recall, it's, for example, things like mining empty blocks. And also there's a tragedy of there might be tragedy of common situations when there's some behavior that's in everybody's interest, so the benefits are shared for the whole network, but the costs are kind of private to the node that is engaging in this behavior. And in this case, we can expect that this kind of behavior will be underprovided. So these are the incentive misalignments that we want to avoid. So the one incentive system, the most basic incentive system that we already have implemented and tested, and you have already listened to a very detailed presentation about how it works. And now I'm going to talk about how swap, all by itself, addresses some of these concerns. So just a quick recap what swap does on a very high level. So in each case, if one node wants something from another node, they eventually pay. That's kind of the bird's eye view of the thing. And of course, the option number one is that they pay by reciprocal service. So typically, they don't pay by sending checks or making on-chain payments. The typical preferred way of paying for service is reciprocal service. If the accounting of mutual services gets disbalanced, then it can still be settled by a payment. And if it gets disbalanced and there's no payment coming forth, then eventually the sanction is to disconnect the node that is running in the red. So I don't want to talk too much about it since you already heard a presentation in the morning. But the interesting part, which I would like to spend a little bit more time on, is what these things incentivize. Like once we have swap, what can we expect to happen? First of all, nodes will try to retain the most profitable chunks. So they want to retain the chunks, they want to store the chunks. It's in their best interest in terms of swap to keep chunks which are requested from them very often. Typically, these are the chunks that are nearest to them, which is wonderful because that's what we want them to do. So swap all by itself incentivizes that you kind of follow the DHT protocol correctly. Because if you are storing chunks that are far away from you, then they're not going to get requested from you, and that's dead weight for you. The other thing that swap incentivizes is in caching. So if there's some popular content that is being requested from you all the time, and even though it's outside of your radius of responsibility, but somehow it gets requested very often, then you can earn money by caching, because you kind of buy it once, you store it, and each time it's requested of you, you're selling it. So actually swap does incentivize caching. So we have some caching code in swarm nodes, and it's not worth for somebody to take that code out, because that caching behavior of the swarm node is actually in the interest of that node through being paid for it via swap. So one consequence of swap being in place is that we can expect popular content to be replicated very broadly and persisted. So if there's some very popular DApp, something like, I don't know, like wallets, like MyCrypto, or some other DApp that everybody uses, then we can count on this content being available forever, because swap actually incentivizes both its storage and its caching. Now there's one thing that we encountered observing what happens, which what we call the donut effect, is that if some content is really popular and it's requested all the time, then it's always served from cache, and it's not actually served from within its radius of responsibility. Which means that selfish nodes that basically keep a tab on every little chunk and count how much that chunk earns them, they might decide that even though I'm the closest node to this chunk, I will still garbage collect this chunk because it doesn't make me any profit. But that's okay. It's okay because while the content is popular, it's served from cache anyway, so the users of the network will not experience any loss of content. And if the popularity calms down, then the syncing process will kind of gravitate this content back to where it belongs. So the content will still persist. So the donut effect does not affect persistency, even though it's an observable behavior. However, syncing itself, the fact that content is being pushed towards where it belongs, is incentivized only weakly by swap. Basically, there are two reasons why you want to sync content. One is that you want to make room for other content. So instead of just deleting something, you rather sync it before you delete it, because there's this common good thingy that if we all do this, then the network will work better and we will kind of all benefit from it. And it doesn't cost much more, or it shouldn't cost, I will talk about it, so it shouldn't cost you much more to sync something and then delete it than just simply delete it. So the fact that you're earning money by swap, therefore you want the network to function correctly, yet you want to make room for stuff that is profitable for you, these two things together weakly incentivize that you push content that is far away from you to where it really belongs. But it's a weak incentive, it's not a strong incentive. And garbage collection. Again, nodes can be expected to optimize their garbage collection strategy to maximum profit. And there's this heuristic that we have implemented. It's the garbage collection queue. So a garbage collection queue is consumed from the bottom. Whatever is at the bottom of this queue gets garbage collected. And chunks that have been accessed recently, they're moved to the top of the queue. Which means that if something gets requested from me, so people actually paid to me, I don't want it to garbage collect soon, so I move it from wherever it is in the queue, I move it to the top. That's one strategy. However, it's very important that syncing does not insert into the top of this queue, because what's at the top of this queue is kind of proven content that has already been requested from you. The stuff that is being synced towards you, it's unproven content, you're not sure, you cannot be sure that it will ever be requested, all of it can be spam, and you don't want syncing to crowd out profitable content. So what happens in practice, and the way these swarm nodes are currently implemented, is that syncing actually syncs somewhere towards the middle of this queue. And what would really help, and we're going to have that, and I will talk about it shortly, is some credible signals, some signals that are really costly to fake, that somehow marks important content, that distinguishes between garbage and spam, and on one hand, and important, valuable information on the other hand. Because if we have something like this, it would actually advise the garbage collection strategy in order to be profitable for the node that does it. So we have arrived to the third part of the presentation. So how do we distinguish spam from important information? And for that, we have come up with what we call a postage stamp model. So it's been inspired by the international mail delivery, how like paper mail is being delivered across the globe for like at least 2 or 3 centuries now, 2 for sure. So upload should cost, like there should, like for upload, somebody needs to pay for uploading, because uploading does impose new costs on the whole of the network, but it's important that only the uploader pays for it. Because otherwise, if those that are syncing the uploaded content would also need to pay for it, they just won't do it. So somehow we need to mark chunks as, okay, this chunk is paid for. And that should be recognizable by looking at that chunk. And so the unit of accounting here is, so the dimensionality is value over information over time. So that's one example, ETH over chunk over second, but it could be anything. It can be like dollar per kilobyte per year or something like that. So the dimensionality of accounting is this. And a very important insight is that because the hash function distributes chunk uniformly across all the nodes, actually the local information that a node has is actually sufficient. It's surprising. So basically, you don't need to see all the chunks marked with the same type of postage stamp, and yet you can have a pretty good guess of how many there are, because you know how large the network is, because you have a logarithmic number of peers. So up to a factor of 2, you know how many nodes there are in Swarm, and you know how many chunks with that particular postage stamps you observe, and you simply multiply that by the number of nodes in the network, and that gives you an accurate estimate, an accurate enough estimate of how many chunks have been marked with that particular postage stamp. Moreover, the inaccuracy that you have stems from the inaccuracy of your estimate from the number of nodes in the network, but that's the same for all types of postage stamps, meaning that in order to compare two different postage stamps, your accuracy of estimate will be better still, because the error that you make with the number of nodes estimate will be the same for both of them, and it will kind of cancel out. So the simplest implementation of the postage stamp, and that's the one that we're going to implement first, is the so-called proof of burn. So proof of burn means that in order to put a postage stamp on a number of chunks, you need to prove that you have spent Ether. So proof of work wouldn't work. Proof of work is a very natural candidate, and we could just take a page from Whisper, which uses proof of work for this very purpose. But the problem is that the delay, the amount of time that you need to spend to generate that proof of work, would be proportional to the file size. So it would be a real drag on the performance of the network. And the other problem is that proof of work has a huge specialized attacker advantage. So if some attacker is specializing in attacking this particular feature, then they have a giant advantage over the regular users who are using general purpose hardware for just using it. So specialized attackers with special purpose machines or special purpose software have a huge advantage, and that would actually become a denial of service vulnerability, because they could spend the network at a much lower cost to themselves than what the legitimate users would have to expend. So proof of work is as attractive as it is, unfortunately it's unworkable. So instead of that, we have proof of burn, which is basically a digital signature. So proof of burn is a digital signature on a chunk with a public key which is registered with a smart contract in exchange for actual payment, which is locked up in the smart contract and not released. So you burn some Ether. In exchange for that, your public key with a expiration date is registered by that smart contract that anybody can check with an access. And therefore, they can check whether you have indeed burned enough Ether in order to put that signature on that particular chunk. So you pay once on chain to this contract, and then you can sign a whole bunch of chunks, but the individual nodes in Swarm will know how many chunks you have signed with that particular key, so they can divide it. So they can tell how much you actually burned in order to sign that one chunk, which is nice because you do only one on-chain operation and you can do millions of off-chain operations. So we are using the blockchain sparingly. Of course, it raises some privacy concerns. The privacy concern here is that if you're doing an upload and you're signing every chunk with the same key, then it kind of indicates that all these chunks belong together. So even if they are encrypted, you don't know the structure, you don't know in what order they follow after one another, but still you know that these chunks, they originate from the same upload, and that can be a vulnerability, for example, for censorship. So if some of these chunks turn out to be whatever offensive content that some powerful entity wants off the swarm, then they can say that, okay, remove everything that's been signed with this key or else. And we want to avoid that. So we somehow want to solve this problem, and we actually do have a solution. I will not go into detail, so we will have this Ask Me Anything part in which I will explain this in detail. It involves a cryptographic primitive called blind signatures. I will talk about them later one-on-one during the Ask Me Anything session. And the next stage after the proof of burn is the storage lottery, which is even better than proof of burn, because it actually allows storing nodes to use the data that they're storing as lottery tickets. So each chunk that has been signed because of a payment to a smart contract automatically becomes a raffle ticket in this lottery, in which the postage that was paid for uploading all those chunks will be raffled off to those who are actually storing these chunks. And this way you can actually strongly incentivize syncing. So at this point, if we implement storage lottery, syncing will no longer be weakly incentivized. There will be a very strong profit motive in storing what you need to store, because we can have these very easily enforced rules that whoever submits a chunk to claim their winning in the lottery, if somebody who has an address that is closer to this chunk also submits it, they will actually win. So they can challenge that and win the prize. So the closer you are as an uploader, so the closest uploader is the one that wins. And because of that, a lottery ticket is suddenly worth much less for the nodes further away than for the nodes that are closer, which means that the node that is closer is willing to pay for it. It's willing to buy it for a price for which the seller is willing to sell, because the value for the two is different. So there's a mutually beneficial exchange transaction that can happen over swap. So you can use swap to pay for these. And suddenly you don't have that problem that who pays for syncing, because nodes actually want to buy the lottery tickets, which give them a expected and calculable, so an expected winning that they can actually calculate. They can statistically forecast it, and therefore they know at what price they're willing to pay. And because of the way it is arranged, the nodes that are further away, they're willing to sell for that price, which creates a market for actually syncing the chunks. And also it solves a large part of the unpopular content issue. So that's the one that has been addressed in several talks, and I will also talk a little bit in more detail about it in the last part of my presentation. So unpopular content is the one that is not asked for from you, and therefore swap does not incentivize its storage. But this lottery, to some extent, does. So in the last part, in the concluding part of my presentation, I would go through a few use cases. 2 minutes, okay, that's enough. So the first and easiest thing is sending large files. So it's nice because the persistency that it requires is on the order of magnitude of days. You definitely get feedback on the beginning of the availability, because that's the progress bar feature that has been talked about already. Possibly the end of the availability, so you can have some estimates of the costs involved, and therefore people at Datafund have already implemented fair drop, for which the kind of incentives that we have in place seem entirely adequate. The next slightly more involved use case is hosting static web content, and most importantly dApps, web-based dApps. So here, for popular content, swap is enough. We have already discussed that. For content that is not yet popular, so you have a startup, you have published the dApp, but nobody knows about it, so you're exerting marketing efforts to make it popular. But before it gets popular, it still needs to be available. It still needs to be persisted. So what can you do? Well, the easiest thing that you can do is you can pay for it by swap. You can pretend that it's popular. You need to download it yourself and keep paying for it. And therefore, those who are incentivized by only swap will host it. That's actually the step 0 of content pinning. So this is something that we're going to have very soon. When you can store stuff that you want Swarm to host, and you just keep re-uploading it and downloading it and pay all the nodes over swap to do that. And because of the garbage collection, the way the garbage collection queue works, it will provide the adequate incentives for Swarm to host it. Then it can be delegated, so you pay someone else to do it for you, or eventually there might be smart contracts around which DAOs organized that are doing this for others. So this is again something that is very well within reach, and we're hoping to get here this year. Persistency against censorship. So here you want to force censors to play and lose whack-a-mole games. So basically you want it for the publisher to be easy to re-upload and for censors to be difficult to get it off.
Tony, short question. We are 11 minutes over the time.
Oh, sorry. Okay, so I have one more slide.
Okay.
So, okay, ask me anything. Storing Ethereum state on Swarm, we have already discussed this. Storing encrypted personal data, so this is this is the holy grail of persistency. This is the hardest kind of persistency. So imagine you have your own encrypted backup. Nobody will ever download it except you, and probably you will not download it ever. So for these, we have these things which are a little bit further down the road. So this is the functionality that probably Swarm will not have this year, but this is where we're shooting for. And the very last thing that I would like to just mention, and because this is a question that I very often get, like how can we delete from Swarm? And we have this fundamental issue that we have. Now we can do it the Web 2.0 way. So what happens if you delete something from Facebook? It gets marked as deleted. Well, we can do that too. We can do that. So basically what deleted means that it's no longer accessible from a given UI or a given API. Also, it might become undiscoverable from the current Ethereum state. Now, since Ethereum state is a eternal record, it might still be discoverable from a past Ethereum state. But also, as we have incentives for garbage collection, if something is not being paid for, the incentive structure that we have in place will mean that Swarm will slowly but surely forget it. So basically, these are the things that we can do about deleting content. So that's it. Thank you so much for your attention.